Hi, and welcome back for part 2 of chapter 2, where we're going to talk about the periodic table. So it's our systematic organization of the elements that we want to say, here's how the elements go together, here's how we can organize them for extra information. And so we go ahead and we order them in order of atomic number, where we start with hydrogen at number 1, helium at number 2, and then we go back until we get all the way to number 118, oganesson, which you don't need to worry about because you will never use it anywhere near a lab. All right, so how do we read that periodic table? How do we look at these boxes and know what they are? Well, we have the symbol in the middle, so there's K for potassium. We have the atomic number above it, so remember that's how many protons it is. And then we have the atomic weight below it, which again is that weighted average of all the isotopes added up by their natural abundance in nature. So when we organize this thing, well, the rows going left to right, we call them a period. And then the vertical columns going up and down are the groups. And elements in the same group, so everything that's on top of each other here, are going to have similar properties. Not identical, but usually very similar. They will often differ by intensity. So a famous one with the alkali metals is that they all react with water. Lithium just kind of fizzles. Sodium kind of pops in a little bit. With potassium, you're definitely going to see flames. It's probably going to fly in the air. Rubidium and cesium, you're going to get a decent fireball. So the farther down you go, the more violent the reaction. But the key thing is, well, they all still react. All right, so that's that periodicity. That when you look at the things going across, you'll see patterns repeat. So we have helium as a non-reactive gas. Eventually you get to another non-reactive gas. And then we get to another non-reactive gas. Immediately after that, well, we have a soft reactive metal, another soft reactive metal, another soft reactive metal. So we see that pattern over and over. And then sometimes we have to add things in when something new starts. And that's why the table gets wider. So we talk about some of the named groups. The ones that you really need to know are the first two and the bottom two. Alkali metals is that first column on the far left, 1A. The alkaline earth metals are 2A. Chalcogens, I wouldn't worry about that name too much. No one really uses it much anymore. Halogens, though, that get used all the time, 7A. And the noble gases on the far right are 8A. So it says these 5 groups are known by name. There's others. 5A is the pnictogens, but we just don't use them all that much. But the top 2 and the bottom 2, those we still use on a very regular basis. All right. So metals are on the left side of the table, and I don't even say the left side and the center. Most of the periodic table are metals. These are the things that are shiny. They conduct heat and electricity. They tend to be solids at room temperature. Watch out for mercury, of course. But they have that in common. They tend to also be malleable and ductile. Remember that from Chem 1. Nonmetals are on the right-hand side. They're in green, also including hydrogen. Remember, that one always gets in there. They can be solid. They can be liquid. They can be gas. So nonmetals have a wide variety of physical state. And then, of course, we have the ones along the stair step. Sometimes polonium gets added in there. Sometimes I've seen acetine added in there. It kind of depends on which textbook or what year it was written. But if it's touching the stair step, except for aluminum, definitely except for that one, then we call it a semi-metal or a metalloid because they have properties that are sort of like metals. They have properties that are sort of like nonmetals. They're in between. So, well, there they are in between. When we then want to talk about chemical formulas, we want to make sure we write it where we say a subscript to the right of a symbol tells you that number. Or the number of that atom. So it's always the number tells you how many of the element that was immediately said. So when it's H2, the 2 applies to the H. When it's H2O, that 2 still just applies to the H. C2H4 down here for ethylene. 2 of the carbon, 4 of the hydrogen. All right. So it says here molecular compounds, often referred to as covalent compounds, pretty much almost always non-metals. Could be 2, could be 3, could be more complicated. But when we see that a lot, molecular compounds almost always non-metals. We also have to watch out for the 7 diatomic elements. So everybody's favorite mnemonic is Brinkelhoff or go to 7, make a 7. But whichever one you want to use, make sure you know these 7 elements. Whenever it's an element here on Earth, they're written with that 2. So hydrogen is H2, nitrogen is N2, oxygen is O2. Got to make sure you know that. All right, so types of formulas. When we write these formulas, what are we going with? So an empirical formula. This is the lowest whole number ratio of atoms for each element in a compound. So it's simplified. It may not be the real formula. It might be. Hard to say. But it's always the simplified formula. A molecular formula is the exact actual number. So if we go back to ethylene, here's an example. That C2H4 is the molecular formula, but the empirical formula would be CH2 because we could divide both by 2 and simplify it. So that's where it's not always the same thing. So it says if we know the molecular, we can determine it's empirical like we just did, but the converse is not true. We can't go from empirical to molecular unless we happen to know what the molar mass is. Then we have a target to go after. But if we only have empirical formula and that's it, we don't know what the real formula is. We can't. All right, how do we draw these molecules? Instead of just writing them, how could we draw them? Well, we have molecular formulas that we just write, but a structural formula, this shows where the atoms are attached to each other, but it usually does not depict three-dimensional shape. So here's a normal structural formula of methane. We have a carbon in the center. Each hydrogen is connected with a single bond. So we have lots of information there. But we can show that three-dimensional thing with a couple different ways. The quick way is with what we call a perspective drawing, where if it's a normal line, we're going to say it's in the plane of the paper. Or if you're drawing on a board, it's on the plane of the board. It's flat. If we have a wedge, like this one here, that means it's coming out towards us. And if we have a dashed line, that means it's going away from us. Now, this book does do the thing that a lot of chemists don't like. I'm one of them, and so was my grad school boss. We preferred it that, well, if it's going away from you, then the dashed line should get smaller as it goes away from you. So if I were drawing this myself on a paper, I'd start with the dashed lines wider and then get more narrow as I get to the H. You're going to see both ways depending on which book you're looking at. It's not going to make a difference. It will not be graded right or wrong either way. We have also, for showing three-dimensional, we have a ball and stick model. So if you ever use the plastic model kits where things snap together, well, that's what that is. And then we have what's called a space-filling model. This attempts to show the molecule closer to how it actually is. So when we look at this ball and stick, we say, oh, wow, those hydrogens are really far apart from the carbon. There's all this empty space in between. But then if we look at the space-filling model, oh no, this is based on actual distances and actual measurements of the molecule. Those hydrogens are really in close to the carbon. There's not a lot of empty space there. So space filling is a very useful tool, especially if you're doing something with medicines, if you're trying to design drugs and treatments for a specific ailment where you say, oh, it's got to fit in this molecule or interact with this molecule in the body. Well, you need to know, well, what's the space filling look like? Can it even fit there? That's how you're going to know. All right. Ions. When an atom or a group of atoms loses or gains electrons, it becomes an ion. Remember, cations are the positive ones. The T can look like a plus sign. This is usually metals. Not always, but usually metals. Anions, or when you gain an electron to get a negative charge. The monatomic ones are usually non-metals. Noble gases don't form ions either way, unless you really hit them with a lot of energy. But you see over here on the right, this is where you have negative ions. Now, notice hydrogen. A lot of times it's +1. It can also be -1. So this is what we would call the hydrogen ion, and this one we call the hydride ion. But either way, hydrogen can go either direction, so just keep an eye out for that one. They note here, these are the ones that they're showing. These are the ones that always have the same charge. So aluminum is always +3. These are always +1. These are always +2. They leave out beryllium for complicated reasons. If you want to assume beryllium is +2, you go right ahead. All right, so here are some common ones. And note here that the bold ones are the ones used most often. You should learn to use them, especially the polyatomic ones like ammonium here. Remember, that's NH4+. But we have hydrogen, sodium, potassium, silver. Note that silver is always +1. That should have been on that previous page. But if you see these ones in bold, learn them first. They come up both in the book and in homeworks, in labs. They're just the more common ones, so make sure you know them. We have magnesium, calcium. Zinc is always +2. Make sure you remember that one as well. And then we have aluminum down there. Now there's a couple here of the transition metals that they want you to know. Know that copper is usually +2. It can be +1. It was back here, but +2 is the much more common one. Iron +2 and iron +3 are both common. Lead +2 is more common. It can be +4, but +2 is common. So these others might come in, but these are common ones. Remember that the transition metals get these Roman numerals, tell you what the charge is. So when you see copper 2, that means +2. Iron 2, +2. Over here on the right is the old system for naming them, and we don't use that anymore because you had to memorize too much. Notice that copper +2 is cupric, but iron +2 is ferrous. It's the iron +3 that's ferric. And if we go back, it's copper +1 that was cuprous. So it's the system of the ic is always the higher charge and the us is the lower charge. But you have to memorize, well, which one is it for each individual metal? And so a lot of people said, hey, why are we memorizing all this stuff? If we just use the Roman numeral, we don't have to memorize. We can just say copper 2, iron 3, and then we don't have to worry about did people remember the correct one. Because remember, we want to be clear in our communication. We want to make sure everyone understands what we're doing and is on the same page. All right. We also have common anions. So notice that lots of the elemental ones, they recommend, fluoride, chloride, bromide, iodide. Also a few polyatomics here: hydroxide, oxide, sulfide, acetate, nitrate, perchlorate, carbonate, sulfate, phosphate. So there's a decent number here. And remember, on the AP test and in college classes, they do not give you a list of polyatomic ions. So if they give you these polyatomics and say you should probably know them first, yeah, you should know them first. You need to memorize them for the test. All right. We talked a little bit about polyatomic ions. These are when you have a group of atoms with a charge. So we have a cation like ammonium. We have anions like sulfate. So again, this should all be reviewed from Chem 1. Ionic compounds. Well, this is when, now we're going to talk about compounds. So if we take these ions and put them together, what do we get? So ionic compounds, they're formed between ions, which means it's usually between a metal with a positive charge and a non-metal ion with a negative charge. And the electrons are transferred between them. So the sodium atom starts with 11 protons and 11 electrons. It loses an electron to get a +1 charge. The chlorine atom, 17 and 17, but it gains an electron from the sodium. Now it has 18 electrons and a -1 charge. And then we just say, well, everyone knows that opposites attract. So you have your negative, positive, negative, positive, negative, positive, negative, positive, negative, positive. They always alternate in all three dimensions. And because of that setup, and we'll talk about this much later in the course, because this cubic setup here, well, that's how we get the cubic crystals that we actually see with salt. So there is a tie between the microscopic and the macroscopic there. Well, how do we know what formula we're going to get for an ionic compound? The easiest way is to say, well, the compound must be neutral. So we're going to kind of go with a common multiple. Well, if we switch the charges, we're guaranteed to get a common multiple. So we take this +2 from magnesium and we just move the 2. We take the -3 and we just move the 3. That tells us magnesium nitride is going to be Mg3N2. The only trick here is, like they say, do the switch. But if the subscripts are not the lowest whole number ratio, divide them to get the greatest common factor. So if it's 2 and 2, we can reduce, simplify, however you want to describe it, to make it 1 and 1. If it's 2 and 4, we can make it 1 and 2. So do the switching of the subscript becomes the charge, and then check, can I reduce this? In this case, no, so leave it as is. All right. We need to do this so we can learn chemical nomenclature. Nomenclature means a system of naming. So for this chapter, we're going to do ionic, acids, some simple molecular compounds, so simple covalent, and then they briefly touch on some organics. Don't worry about the organic stuff here. We're not going to be discussing that other than for AP chemistry, just knowing if I see an OH group on a carbon chain, it is an alcohol. All right, so inorganic nomenclature. So when we have these compounds, this covers ionic and covalent. If it's ionic here, we're going to write the name of the cation. If it has more than one possible charge, we write the charge with a Roman numeral in parentheses. If it's a polyatomic cation, it will end in ium, so ammonium. There's a few other ones, but ammonium's really the only one that they're ever going to use here, so don't worry about that. If the anion is an element, change it to ide. So we would write, oxygen becomes oxide, fluorine becomes fluoride. If the anion is a polyatomic, you just write the same name. So that's actually the same thing here. They're just telling you, oh, it's a polyatomic cation, ends in ium, so do a whole bunch of metals. But if you have an anion that's polyatomic, just write the same name. So carbonate, write down carbonate. Sulfate, write down sulfate. Chlorite, write down chlorite. All right. Now, how do we know that? Well, you notice I switched to ite there at the end, because if we have to memorize a bunch of these, how are we going to know the pattern? So if you have two oxyanions, meaning an element with oxygen, and they have the same element, the one with fewer oxygens ends in ite, the one with more oxygens ends in ate. So nitrite is NO2, nitrate is NO3. Sulfite, SO3, sulfate, SO4. Again, here there's some memorizing that you have to do where it's like, well, wait a minute. In the second row, you can kind of go with there's a maximum of 3 oxygens. In the fourth row, there's a maximum of 4. But then we get things like this chlorate. Well, it's not chlorate, it's perchlorate. What's going on there? We'll talk about there. The other pattern to note to help you try to remember some things, the charge increases as you go from right to left. So if the chlorine oxyanion here is -1, then the sulfur one is going to be -2, the phosphate one is going to be -3. If we go up here and restart here, nitrate is -1, carbonate's -2. So it always goes up left to right, but it doesn't start at the same point. So some of these shortcuts, you kind of have to figure out if something else works for you, feel free to use the something else. All right, now let's go back and talk about this perchlorate. If there's 4, or actually if there's 3 or 4, the one with the second fewest oxygens ends in ite, so ClO2- is chlorite. The one with the second most ends in ate, so ClO3 is chlorate. When we have the one with the fewest, that's where we use hypo, and still with the ite, so ClO is hypochlorite. And the one that has the most oxygen starts with per, so perchlorate. The way I like to remember this, hypo is the same one we use for medical conditions such as diabetes. If someone has very low blood sugar, they are described as being hypoglycemic. So very low blood sugar. So hypo, oh, it's got very low amounts of oxygen here. Per is coming from the same prefix as hyper, meaning there's lots. So someone who's hyperactive has lots of activity. If you're hyperglycemic, you have high levels of blood sugar. So perchlorate has the highest levels of oxygen, ClO4-. The good news, this basically only happens with the 3 halogens that are the third row or lower. So you'll get the same pattern for perchlorate, perbromate, and periodate. They all happen with those the halogens, and they're the only ones it really happens with. There's a few others where it comes in with like permanganate, but usually you can focus on just the halogens for this, and it does not apply to fluorine. Fluorine does not make these. All right, so that's the pattern I like to use to go with these 4. All right, let's talk about acids now. So it says if the anion of the acid ends in ide, which means it's probably coming from an element, change the ending to ic acid and then put hydro in front. So HCl, well, chlorine, the anion would be chloride. Okay, hydrochloric acid. This would be bromide, hydrobromic acid. Right? If it ends in ite, change the ending to us. So I don't know why the space is here, but HClO, hypochlorous acid. HClO2, well, ClO2 is chlorite, chlorous acid. If it ends in ate, just stick it with the ic acid, but don't put hydro in front. So HClO3, well, ClO3 is chlorate, make it chloric acid. ClO4 is perchlorate, make it perchloric acid. So they give you a nice little summary here. If you start with the various anions, how you can get to your various acid names. Going backwards is the same thing. You say, oh, if it starts with hydro, then I know it's an anion that ends in ide. If I see us, then I know it was an ite polyatomic. If it ends with ic and it doesn't have hydro, well, then I know it was an 8 polyatomic. So you can just kind of go look for that. All right, now for the binary molecular compounds or binary covalent compounds, the name of the element that's farther to the left in the periodic table or lower down the same group is usually written first. Basically, it's whatever way the formula goes. The real reason is we go with whichever one is lower in electronegativity, but since we haven't learned about that yet, we'll get to that later. But that's why they're saying it's usually the ones that are more to the bottom left will usually go first. That's a pretty good assumption. And then we use prefixes to say the number of each, but we do not use mono with the first element. And so when we have things like CO, well, we'd say carbon monoxide because there's one carbon, but we leave the mono off. But there's one oxygen, we don't leave it off the second element. So here's our 10 prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Right? So the second element, we still change to ide. So CO2, carbon dioxide, CCl4, carbon tetrachloride for 4. And then it says, if the prefix ends with A or O, and the name of the element begins with a vowel, the vowels are often elided into one. I don't like the way they wrote this. I'd say if the anion, or if the second element is oxygen, then it's the A or the O gets squished into one. If it's iodine and becomes iodide, we will write triiodide with 2 I's in a row. So I don't like that. And whether it's a tetraiodide, yeah, we'd still write tetraiodide. We wouldn't smash them together. But with oxygen, we'll chop off the A or the O because that O sound from oxide, it makes the word flow. So dinitrogen for N2, pentoxide, we only put the 1 O in there. Carbon monoxide, just the 1 O in there. All right. And now very, very briefly about organic. I think most Chem 2 classes got here before the work from home happened last semester. Or if you're watching this video in a later year, remember that thing. Oh yeah. Or if you had an earlier Chem 2 class, then you should have gotten to this. They just say, oh, meth, eth, prop, and then they stop there. So you can see this is a very basic thing. The main thing they're going for is if it ends in ane, it's probably just a simple hydrocarbon. That's all I want you to know. But then if it's an alcohol, if there's this OH group, then the name changes. You chop off the ending E and put the OL at the end. This will actually be important on the AP test. They have a habit of asking questions about some later on topics where they'll say compare these two molecules and maybe it's ethanol or maybe it's 1-propanol, and you have to remember that that OL ending means there's an OH, and it's that OH that's going to be what you're talking about in your answer. So the main thing, just remember alcohols end in OL, and they have this OH in the structure. And when you've got that, well, that's all we need to worry about for nomenclature of organic compounds at this point, or actually for most of the course. So good luck. That's the end of Chapter 2. Almost the end of Chapter 2. Depending on where we put things, we can have isomers. That often comes up with organic, but again, not going to be a huge difference in this course. We'll have a little bit of talk of that for intermolecular forces, I think, but not much. So that now is the end of Chapter 2. So you can end the lecture here or go back and get the notes you missed, and then do whatever homework or other assignments you've been asked to do with these lecture notes. Thanks.